So good morning. I hope you're all a bit more awake than I am. This has been an ongoing project trying to put together some of the measurements from between Pepsi and SWAP, our two particle instruments on board New Horizons. And of course, one of the things that we've been trying to do is to really understand the heliosphere. And we don't have that many instruments, of course, that are out in this region. Turns out that New Horizons has been an excellent carrier for being able to get us out to look at this area and how that the solar wind goes ahead and evolves as we're going out toward the termination shock. Um, and this sort of summarizes some of the measurements from the two. Basically, of course, what we're able to do with SWAP and with the SWAP team is to be able to look primarily at the solar wind, but also we can see the so-called pickup ions. These are the ions that are formed at relatively higher energies due to neutrals coming into the heliosphere from the interstellar medium. And with Pepsi, of course, we're looking at much higher energies with a solid state kind of a detector that also does time of flight. And again, we're seeing what appear to be pickup ions at much higher energies, as well as so-called superthermals, other particles that are being accelerated. And so one of the questions is to what extent that one can actually try to overlap the two de facto energy scales. And this was certainly not something that was built in from the beginning of this mission. But it was sort of a happenstance that we've been trying for a long time to take advantage of. It's been an old problem because basically what one is looking at with solar wind is a high flux of particles, it's low energy, whereas with the much higher energy energetic particles, we're looking at very low flux, high energy particles. And trying to put all of these pieces together is very difficult to do with the technology. You just don't have that many orders of magnitude in the dynamic range typically in either the energy scale or in the intensity scale to be able to make the measurements. It's always been a problem. It was a problem on Voyager. For a long time, we had the plasma instrument, of course, on Voyager, and we had the LECP instrument, Tom Cremigis's instrument on board Voyager, going through all the magnetospheres of the outer planets, as well as going through the heliospheric medium, and now actually into interstellar space. And there was always this gap in energy coverage, and it led to a great deal of arguments and discussions at a great many meetings and in the literature about, well, what was really going on between. And everybody was always like, well, wouldn't it be nice if, and of course, the if was always there. So we've got that similar issue on New Horizons and with Swap and Pepsi, and the question was trying to put the pieces together. This is just a schematic, and I've shown this one before. Matt Hill's shown this one before as well, kind of showing you where the various areas are, trying to get between the energy of the solar wind with a peak at its with SWAP, and then with this fall off in energetic particles with Pepsi. And that's always been the problem, trying to put those together. And Peter Coleman was actually the one that did a lot of work along with Matt Hill, about trying to extend the Pepsi response to these lower energies. So Pepsi is an energy by time of flight experiment, which means we're measuring both the speed of the particles as well as their energy. Once you get below about 30,000 electron volts, the solid state detectors don't work anymore because of the physics of that interaction, just inherently in solid state detectors. But we can still actually measure how fast the particles are going. We just don't know what the particles are. And in principle, I can have both helium and hydrogen that's coming in, but I don't really have any way of separating those. So certainly one of the things that we've been trying to do is to take a look at both the Pepsi and the SWAP data. It turns out if you look at these two swaths, there are the shocks nicely line up with each other, where that you can see the discontinuities, and we see that over and over again. Um, This is from this is an example swap spectrogram. This was published by Dave McComas, I believe, in his paper in 2021. And what you're looking at is this combination of here's the solar wind protons, here's the solar wind helium. These are the pickup hydrogen, and then there's this sharp cutoff at about twice, an energy that corresponds to about twice the solar wind speed. And then there's another shelf down here that is sometimes present in the swap data. It depends on how fast the wind speed is, which has been ascribed to being helium plus pickup. Again, helium coming in much lower levels, but going up to a much higher energy, up to about the cutoff of the swap instrument at about 7.8 kilovolts, which just barely or overlaps just a little bit with what we can see down to time of flight measurements with Pepsi. Now, one of the things that we ended up doing, and again, Peter's the one that really gets the credit for all of this, is we've actually got an accelerating potential on the front of the instrument. And so, depending upon what you're doing with looking at the Pepsi raw data and trying to sort of match it up with these various features on here, it turns out you've got a much better fit if you're really looking at helium plus rather than protons. And that makes sense because the helium's heavier and the microchannel plates that are giving you your time of flight signal from going through some very thin films and knocking electrons off actually tend to be more responsive when that I've got the electron showers coming off of something heavier like the helium. So one of the things that we tried to do, and again, Matt and Peter both got back into the lab with the engineering model, trying to put together an efficiency curve for Pepsi and extending it down to lower energies. And you can see the little dots here are the measurements that were made, and this is a logarithmic scale. So there's a lot of scatter. And as I got down here to an ambient energy of about around 10 kilovolts or so, and again, remember the high energy on swap is at about 8 electron volts. There's a lot of uncertainty. We didn't have a chance to actually put the flight unit into the beam line that we had here at APL for doing tests before flight. Because as Alan mentioned the other day, we were in a little bit of a hurry trying to get everything together to get this launched. And I remember at one point, I don't know if Alan remembers this or not, but we were running a little short on time. And he told me that if I didn't get the instrument delivered soon, we would fly a brick instead. And it was it's when that's coming from the principal investigator and you've got a flight coming up, launch coming up, it's marvelous motivation to try to go ahead and get out of the thermal vac chamber, and you can worry about trying to do calibration arguments later. So anyway, this is actually from a couple of years ago, and this was sort of the first attempt that we'd made on trying to put these together. And there's a reason for me mentioning this history. So this was from SWAP. This was from what we had from Pepsi, and we sort of had this sort of vague overlap here, and that's where things were kind of hung. Since that time, I've had a chance to talk more with Pavel Swaksma and with Heather Elliott on the SWAP team. Peter's and Matt have both been doing some more work, and I can't show you the updated view graph because the updated view graph is from the data that I just put together at 8:57 a.m. this morning. And since we have everything electronically and no longer have view graph machines with pins, I couldn't redraw any of this. But it turns out that with Pavel's simulations that he's been doing, looking at the places where that we've actually got measurements in SWAP that show the pickup helium plus, and looking at exactly the same time frame for Pepsi. And this is some work that Peter put together. Finally finished putting together some analysis on that 124-hour period this morning. And it turns out that the Pepsi numbers where that we've got overlap are high in flux by a little less than a factor of 3. Now, sometimes factor of 3 sounds like a lot, but when you're doing particle instruments and you're out in areas where that your calibration's not very good, 3 is a pretty darn good number. So Pavel has actually put together a lot of the analysis of where that the pickup ions are. We've got the analysis that's put together with the things from Pepsi, and I think that this is going to give us enough that we can probably, he said, probably automate all of this so that we can actually get a good run of the data. But again, basically, trying to do the calibrations on these time of flight instruments is a really tricky business, especially when we've got some mixture of protons along with helium at some level. And whereas with swap with the electrostatic instruments, you've got a much better measurement of exactly what you're getting in at that energy. And so, effectively, this is giving us a way of doing a double check on, how well that we were able to actually calibrate Pepsi with the engineering unit after launch. And I think we can pull, with the two teams working together, we can pull those numbers together. And we're actually going to be able to put together this distribution function that's going to go all the way from the solar wind uh, out to fairly high energetic particles. Matt's been doing a lot of work actually getting us out to galactic cosmic rays with Pepsi, again with some of the capability that is built into the instrument, but is certainly nothing that we planned on using before launch. And so, this is again, I think one of the earmarks of the New Horizons mission, that we have been figuring out ways of doing things that we really hadn't planned on because before launch, because they weren't focused on those science questions. But once that we got this instrumentation up there, we've been able to go back and put a lot more of the story together, a lot more of the physics, and really a lot more understanding. And we're going to be able to keep on doing that with the heliospheric phase of New Horizons. And we've got a good, healthy spacecraft, and we should be able to get all the way to the termination of shock and past. And with this capability, which did not exist on the Voyagers at all, it's going to give us really some new insight into what's going on out there. And so I think we can do all of this. We've really got a new window into the heliosphere, I think, as a result of finally getting this together and me finally getting my act together on this. I had some other things I ended up doing last week that ended up when I was going to be doing this analysis, which ended up taking up some time. But I did finish it this morning. So I've got the sanity check at least. And again, we're going to be able to hopefully keep New Horizons running until 2050. That's going to take us into regions where we just don't have those measurements yet, at least. And of course, the best ones right now are with Voyager 1. It's the furthest thing away, but it's also a little long in the tooth as well. So we'll keep going on out there, keep plunging forward. And, I always like putting this up about never ceasing from exploration to really understand where we're coming from. I was really struck with Ed Stone using this with the Voyager missions. I think that the first time I heard it from Ed was right after we'd finally gotten past Neptune and we were on our way on out of the solar system. So anyway, thank you so much for your attention. Work in progress.
We have time for one or two quick questions.
Ralph, what's the current best estimate for how far the Voyagers can get, to what year and what distance still operating, returning data?
I'm sorry, Alan, say again?
How long are the Voyagers going to last? What's the best estimate currently?
I think we might be able to get, I think I had on there, I think we might be able to get out to 220 AU. Right now, the Voyagers are, they're hanging in there. We'll be out at the 50-year mark in 2027. And so whether we're going to keep running with these particular instruments past then, I don't know. We're starting to have to turn off instruments now. Probably the last thing that will go off will be the plasma wave instrument because it uses the least amount of power. But this is certainly going to help us fill in a huge gap that we just cannot get to with the Voyagers at all. And so New Horizons really is the star that's out there for, really continuing and pushing forward on heliospheric science.
Thanks, Ralph.